So having talked about what entropy is, let's come back and see how we want to calculate how entropy changes in a calorimetry problem. We talked about two specific processes, the latent heat process and the specific heat process. And let's look at each of these, and we'll start by looking at the latent heat process because of course it occurred at a constant temperature. And so it's a little bit easier. It says that the change in entropy for your system as it goes from some initial to some final state that we'll simply label the initial state A and the final state B is going to be given by the energy transferred into or out of your system as heat divided by the temperature. Well, we know for a latent heat process that the energy that your system either absorbs or releases is calculated by plus or minus, depending on whether your system absorbed in energy as heat or released energy as heat, the mass of your system times particular latent heat value. And so if I want to put that together, that simply tells me that calculating the change in entropy during a latent heat process is going to be given by plus or minus mass of the substance, the latent heat value that corresponds to the phase transition the substance underwent, divided by the temperature at which that phase transition occurred. So if we look at an example, let's say we have ice melting. Well, I know the energy that the ice had to absorb as heat to melt is given by plus, it took that energy in, the mass of the ice times the latent heat of fusion, and I know the temperature that occurred at was the melting temperature. I can calculate out the change in entropy for ice as it melts by taking plus mass of the ice times latent heat of fusion dividing by the melting temperature, and the thing I have to remember is that that melting temperature must be given in Kelvin. If we're looking at this example and you make the mistake of plugging in the melting temperature in Celsius, well, obviously that's 0 degrees Celsius. Trying to divide by 0, when you try to plug that into your calculator is going to say, I can't do that. Your calculator is trying to help you out by letting you know that you're using the wrong unit. You don't want 0 degrees Celsius, you want 273 Kelvin as the value that you need to plug in to make that calculation. The second process that we've been talking about with calorimetry problems is a specific heat process. And of course, here's where the temperature does change. And we know that we can calculate out the energy taken in or given up as heat during a specific heat process by mc delta T. And if we choose to, we can pull the plus or minus outside of that delta T term. And so we've got plus or minus the mass of your substance times the specific heat of your substance times, in this case, this is the absolute value of the temperature change, so this is the hot temperature minus the cold temperature. If we want to calculate the entropy change during this process, that works out to be mass of your substance, specific heat of the substance, times the natural log of the temperature it ends up at in state B divided by the temperature it started at in state A. If the temperature decreased, then the temperature of B is less than the temperature of A. This ratio of temperatures is a number between 0 and 1, and numbers between 0 and 1 are negative when you take the natural log. So with this first equation here, the sign is tucked inside the natural log term. Of course, we know what sign our entropy change needs to have because it has to have the same sign as Q. And so since we know what sign needs to be out front, we could choose to take care of the sign, then we just have positive mass times positive C times the natural log of hot temperature over cold temperature. That's always going to be larger than 1. The natural log of a value larger than 1 is always positive. Again, as an example, let's say we've got hot water cooling to room temperature. So I know that Q, in calculating if I wanted to calculate Q, the energy that the water had to give up as heat as part of this process, that's going to be negative mc times the absolute value of that temperature change for the water. And so calculating out the entropy change, again, I can do it one of two ways. Mass of the water, specific heat of water, times the natural log of final over initial, so room temperature divided by the initial temperature the water started at. Or, again, I know that this natural log term right here is going to be negative. I pull that minus sign out front because again the minus sign here and the minus sign here have got to be the same, and then it's mass of the water times the specific heat of water times the natural log of hot temperature, its initial temperature, divided by cold temperature, that was the room temperature. Got to remember, of course, these temperatures have to be given in Kelvin. So that's how we would calculate out the entropy change for the water. What if we were interested in calculating out the entropy change for the room? And so in this case, we would treat the room as a heat reservoir. The nice thing about a heat reservoir is that it stays at constant temperature. So I'm back to my entropy change calculation is equal to the energy taken in by the heat reservoir as heat divided by the temperature at which that heat reservoir sits. That from conservation of energy, the energy that the reservoir took in as the water cooled has got to be equal to negative the energy that the water gave up as part of the cooling. So that means in terms of doing this calculation for the entropy change, it's true that that's the energy taken in or given up by the reservoir at the temperature at which the reservoir sits. But the way that we end up doing the calculation, of course, is that the energy transferred to or from the reservoir is negative the energy given up or taken in by the system. And so here's a situation where if you think about our example, and I want to calculate the entropy change of the room as the water cooled, well, I know that the energy taken in by the room is equal to negative the energy given up by the water as it cooled, so that's negative mass of the water, specific heat of water times the temperature change of the water. The temperature change of the water is negative, so that negative tucked inside delta T is going to cancel out with the negative sitting there. So what I can do, of course, is choose to take care of the sign out front, and then I'll just treat this as the absolute value of the temperature change for the water. And so to calculate out the entropy change for the room, what I have is I have a calculation for the energy taken in by the room as heat over the room's temperature. And so what can be a little bit concerning about this equation for students is this: we started with something that looked a lot like our latent heat equation because, of course, the heat reservoir sits at a constant temperature. But we plugged in a specific heat calculation for Q. So just make sure it's clear to you why that's what we want to do in the specific example where we're calculating the entropy change for a heat reservoir. You can leave the temperatures in Celsius to do this temperature change calculation, but the temperature of the room has to be given in Kelvin. So whether you calculate delta T in units of Celsius or units of Kelvin, you get the same answer. But obviously when you plug in the temperature of the room to calculate out the change in entropy, that has to be done in Kelvin.